Okay, this is a small section at the end of two-dimensional motion. It technically is two-dimensional motion. Idea is that now we're looking at something that travels in circles. Again, x's and y's. So technically, this is two-dimensional motion. But we're going to handle it kind of on a limited basis here, and really only one particular thing we'll talk about. We'll come back later in future chapters and deal with this and talk about more specific things with it and circular kind of forces. Okay, as you recall, we did this slide in the previous section. We had an idea that acceleration, which is a vector, is made up of the difference between final velocity and initial velocity. Each one of these are vectors, so when we do this acceleration calculation, we're subtracting two vectors. And whenever we subtract a vector, it's the same thing as adding a negative vector in this case. So this is the same thing as final velocity plus the negative initial velocity. So I have my initial velocity here and my final velocity here, and basically something is kind of, let's say, turning like this, right? We're just taking 2 points like here and then here, and we're taking the kind of average kind of between what's going on. It's kind of rough estimate. So when I subtract them, I add the negative part. So this is the same thing as negative vi. And so when I do that, I add final velocity plus negative initial velocity. So I'm going to move this over here. So this is also roughly about right there. This is also negative vi. And I did tip to tail, so those are added. Alright, so I moved over there, and then the resultant is from where I started to where I end, and that's going to be the direction of, that's really my delta v, which is direction of my acceleration. Alright, so what this is showing me is that while going to the right here, in what in reality is a circular turn, we're just taking two little segments, I have a acceleration that's kind of inward and to the right. And if I drew it over here, it'd look like this, right? Alright, so let's apply this on the next slide to a complete trip around, right, and see how that looks. Okay, so here's a slide from the picture from the book. So in this case, it's going, let's see, counterclockwise. So let's see, say I have a spot here, and then I move to here, which means my velocity is in this direction. Right? After that, you can just say another second later or something else like that, or however some amount of time the object is here, which means my velocity vector is in that direction. Then here, then here, then here, then here, right? You call this some dodeca, hedron, whatever it looks like. How many sides would it have? Decahedron or something. But really, what it's representing is some kind of continuous circular motion, right? But it's just taking the intervals in between, and not every single split second from it. So if I continue on this, right, the direction of the acceleration is the same direction as the change in velocity, because time, right, delta v divided by time, the time doesn't change direction, it's just a scalar. Alright, this comes from, a vector. So this is really where the direction comes from. This is just a scalar. So acceleration delta v over t. And so if I track my delta v's around, so this is where I have final velocity minus initial velocity. That's using this. Let's switch this one around to be here, and I add this one, and to the negative of that, and this is what I get: a inward, right, an inward or to the left change of velocity, which means a to the left acceleration. Alright, if I do it with this one, I'll do final minus initial, This is my initial, final minus this, right? So that's my minus v2, and I get an acceleration this way. Do it again, minus, negative this one, right here, right? Always, right? And so what you see is a continual inward acceleration, and it's pointing right to the central point, right? Continual inward acceleration. Now, at all of these things, if you look at the length, this length of this arrow is the same as this one, which is the same as this one. They just point in different directions. So really what's happening is my velocity is changing because my direction is changing, right? But my actual speed, the length of this arrow, is not changing. So if I am moving in a circle with a constant speed, I am accelerating because I am changing direction. And what is the direction of that acceleration? At all times, that direction is inward towards the center, right? What we call this is centripetal acceleration. Centripetal acceleration. An inward acceleration. And this is an acceleration that is only due to change of direction, right? The actual object is maintaining the same speed, right? The speedometer, if this was a circular track, would read the exact same thing as it traveled around. But the fact that it's changing direction means that there's a change in velocity, because velocity is magnitude and direction. And since there's a change of velocity, there is an acceleration. That vector is always inward. So if I take away all the segments, I get a smooth circle here, and you can see at any given time the velocity points tangential to the circle. So the velocity is tangential, and so at all times you have, let's see, match the colors up a little bit. So at all times you have, a tangential velocity, right? Tangent to this, right? So it goes off in each of these directions. Tangent, right? So if you were to, something's going in a circle and you were just to stop it from going in a circle, if this is a ball on a string, you cut the string, it goes off in a single tangent line like that. But because it's going the same speed, it has a constant inward acceleration, right, that's given here, right? So this always points inward, and even here, it point inward, here, point inward, same thing here, and that is the centripetal acceleration. Okay, we're not going to go into derivations or anything else like that on this one. We'll come back to more circular motion in the future, quite a bit more. But the magnitude, right, this is really a magnitude of this centripetal acceleration is determined by the speed of the object, which is right here, and the radius of the circular motion. Okay, and the direction is always towards the center of the circular motion. So again, this will tell you the magnitude, how long the arrow is, but the direction is determined by where you are. Like here's the velocity, here's the acceleration. Okay, and that depends on the speed at which you're going and the radius of the circle that you're traveling in. Right, so if you look at the two, for centripetal acceleration, which one matters more? Your speed or this radius? And you can see here that this term is squared, so the speed that you're going on matters more for centripetal acceleration. The radius, right, doesn't matter as much because it's not squared. Also, you see that if I increase my speed, right, my centripetal acceleration will increase if I keep the same radius. If I keep the same speed on a smaller radius like track or something like that, if this decreases, then my centripetal acceleration increases. If this increases as a wider track or bigger circle, then if that increases, then this will decrease. It's an inverse relationship. Okay, here's an example, 3.14. Short track speed skaters can cover a distance of 500 meters, that's really one lap, in the race in 45 seconds. At the turns, there is a turn radius of 11 meters. Estimate the magnitude of the skater's centripetal acceleration. So here's what the track looks like, flat, and then it's kind of like an oval track like this. Okay, so the ends are like semicircles, right? And then you have your straightaways. So it says the entire distance is 500 meters, and it's done in 45 seconds. So one thing that we are going to assume is a constant speed throughout the entire trip. All right. So if I want to know speed, that's equal to my distance divided by time. Distance is 500 meters, and time is 45 seconds. So 500 divided by 45 500 divided by 45 means 11.11 meters per second. Okay, that is my speed around the track, or you say velocity, or absolute value of my. So erase that, make that better. So that's like my speed, as in the absolute value of my velocity. All right, independent of direction. So essentially, here at the edges, there is a turn radius. Zoom in here. Right, a turn radius of 11 meters. So this radius right here, right, in all these directions, is 11 meters. Okay, that's R. And so at this point right here, they're going that speed of 11.11 meters per second. Okay, and so now I have a radius, and I have a magnitude of my velocity here, right, or speed. So my centripetal acceleration is equal to speed squared divided by the radius. So 11.11 meters per second. Oops, get rid of that. Let me get through here. Okay, try to erase that squared. Okay, I can't, so I'll just scribble it out. So 11.11 meters per second divided by a radius of 11 meters. This value at the square. And so when I do this, 11.11, and I square that value and divide by 11. And I get a centripetal acceleration of 11.22 meters per second squared, with sig figs probably somewhere around 11.2 or 11 meters per second squared. So most of these right now are pretty simple, as in I find the speed, I plug it in, and I find the radius, or to find the centripetal acceleration, or I know the centripetal acceleration and I know the radius, so I find the required speed or something else like that. But eventually we'll get into more circular motion things as we go along.